Okay, good morning, students. It is Thursday, March 5th. We are on a snow day, and I'm going on the expectation that maybe we won't be here tomorrow on the 6th either for class. So I'm going to go ahead and want to talk about a few things. So I'm going to switch off of me, and I want to talk a little bit about the Hofmann elimination this morning. Let's look at an example here again. So I've drawn up a amine. This is actually a secondary amine, as we can see, a cyclic secondary amine. And then in a Hofmann elimination, we always have a alkyl halide. Methyl iodide is often used, but doesn't have to be. That's used in excess. And then we'll use silver oxide to generate the hydroxide ion that's going to carry out the reaction. So I'm going to stop for a moment. So now we see here that once the alkylation takes place, over-alkylation, we've got a quaternary ammonium salt as the iodide salt. With the silver oxide added in water, it's going to cause us to precipitate silver iodide, and we'll end up with silver hydroxide, and then the hydroxide can then attack the, with heat, attack the beta hydrogen, right, or a hydrogen on a carbon there, adjacent to this. So we can see we've got our two alpha hydrogens there, alpha carbons. So we should think about with this one, which one of those two, either the one straight on top of the nitrogen or to the left, adjacent to the ring, which one of these would be preferable to for that hydroxide to deprotonate. So let's look at this a little more, right? So I've drawn in the hydrogens, and I've shown that silver iodide precipitates. So then our hydroxide ion is going to attack. We need to take a proton, and then we're going to push a pair of electrons to break that one of those carbon-nitrogen bonds. We're still going to have an amine hanging on. It's going to be a tertiary amine hanging on this molecule in this example. But once we do that, we should generate an alkene, and we should be able to see that the bottom part there, that carbon, can't make an alkene right off of benzene ring. So that one's not going to happen. So I'll show you what happens next. So now, students, you can see that the hydroxide has to attack the beta carbon. And there really is only one beta carbon with a hydrogen here. And you can see where that's going to attack in this case. We push our pair of electrons from the carbon-hydrogen bond to make the pi bond. Push a pair of electrons from the carbon-nitrogen bond to give a lone pair. And then the structure down the bottom on the green, we can see that in this case, since we started with a cyclic amine, we're going to end up with the amine still attached in this case to the molecule, and then an alkene. Obviously, in the presence of water, right, if we were to acidify this thing, we might end up having another reaction take place for an alkene. Remember, we could see before a hydration, put an alcohol on there. So it could start with something up like this and do a Hofmann elimination and see how that could take us to something completely different. I'm going to stop here and we'll go on with something new. So I'd like to set this next example up as a problem here. So let's look at this. If we wanted to make 1,3,5-tribromobenzene, how would we do that? Right, from benzene. We can't start with benzene and go just brominate because we see a problem right away that bromine groups, halogens, are orthopair directors and deactivators. So how can we do this? So we should remember that one way we can do this is we can put a strong activating group on a amine group, and then we can use the diazonium route in order to remove that amine. So I'm going to show you that schematically, and then we'll walk through it real quickly. Okay, students, now I'm going to quickly walk you through this here. So if we start with benzene, we can nitrate benzene to make nitrobenzene. We can reduce that in one of many different ways we've talked about already to form aniline, which is a strong activating group. And remember, we can brominate aniline even with just bromine. But if we use a Lewis acid like FeBr3 and enough of it, we can go ahead and tribrominate aniline in the orthopair position, so we can get 2,4,6-tribromoaniline down at the bottom left here. If we treat that with sodium nitrite and HCl and do a diazotization reaction, we can make the azo salt, and that should actually be the with the chloride counterion not shown there in this case. And then if that's a good leaving group, so in the presence of a acid like hypophosphorous acid H3PO2, we can replace that N2 that leaves the leaving group with a hydrogen and get back to now 1,3,5-tribromobenzene. So there are a lot of different ways we can make use of diazonium salts, and then there are a few more that you see in the chapter. If you look at the sections there, we can make what are called azodies, azocoupling reactions. So I expect you'll look at some of that. That pretty much wraps up what I'm going to cover right here in this video. I would encourage you to look at the sapling problems. Remember, we have a sapling exercise due Friday, March 6th. That's tomorrow, as when this is recorded, at 6 p.m. So please get started on that if you haven't. I know a lot of you have. And then have a great spring break in case I don't see you tomorrow on March 6th. Thanks, and have a great day.